as Colin said, it's, well, not just microservice architecture, but the subject of this talk is essentially to take a look at how to use microservice architecture to facilitate a certain way of teams working together. So to give a little bit more introduction, so IBM Watson and IBM Research are separate organizations, and they have, as different organizations, they have different goals, and they collaborate often. And every time a new collaboration starts between these two organizations, two or more teams, sometimes usually two, need to find a way of working together well. And so an observation after my team went through this a couple times, we observed that these teams from different organizations, they tend to have different norms, habits, ways of working, and those tend to align with the incentive structures inside those organizations. So this will be a case study of one approach we took to establishing a development process when a new collaboration of this sort starts. And in particular, we try to do this through system architecture rather than any sort of necessarily agile methodology or whatever else, what flavor of it may be popular at the moment. And starting with the case study, some sort of attempt will be made to extract some principles that could be reused in a more general situation. So as a sequence of topics, there's a couple concepts I want to introduce, starting off with quality attributes and organizational incentives. From there, microservice architecture and architectural hoisting. With those definitions in mind, I'll go into a case study. So as I said, this is between IBM Watson and IBM Research, but the general framework I feel should be able to be reused for just generally teams with different specializations as a more general sort of mindset. Of course, how it actually turned out, because stories are nice, but results are better. And of course, how we could have improved what we did, because obviously this is in hindsight and we were figuring it out as we went along, and some time for questions and discussion afterwards. So first, let's define quality attributes and organizational incentives to help set the stage. But I want to do this in a particular way. So has anybody heard the phrase research code? Who's been sitting here? We actually have a couple of hands. I was starting to think this might be kind of an internal IBM thing, but apparently not. So the general concept, if you haven't heard that phrase before, it's the same concept as prototype code or proof of concept code, those sorts of things. And it essentially refers to code that looks like this. So single variable. Question, because it's not bad code. It's code written for a specific purpose. So with that, to define, we can use that as a starting point to go into the quality attributes of a system to rephrase this in a different vocabulary. So the quality attributes of a system are the various factors which affect its behavior, usability, and design across all components. And there's actually an ISO standard for this, I found out while putting this talk together. I've never personally referred to it, but it has a nice categorization here. So to go back to it, from this perspective, we can say that research code of the sort that I mentioned is generally code that's written for accuracy in the sense of an artificial intelligence application in this particular case, meaning do the predictions it makes, are they accurate? Do they bear out? And it's generally not written for, say, maintainability, among others. And often we have this, we often have this trade-off between different quality attributes. For example, performance and accuracy. Often we would come across a case where a more accurate algorithm would be, of course, often less performant, meaning slower. So the situation that we had is a research organization where the structure of the organization or its incentives are generally geared towards incentivizing publishing improvements on the state of the art in an academic journal, not on shipping performant, maintainable code as a software product. I found actually this old organizational chart of one of the three companies 100 years ago that merged to form IBM. And you can see that this already was a large organization. So you can easily imagine different groups of people forming different working habits or emphasizing different particular aspects of a system. And this only became more true over time, especially as organizations get bigger. In fact, apparently when Watson got started as an organization and people were coming in from other organizations, there was a clash of vocabulary even, where people were trading off performance and performance, because the researchers would call the accuracy performance, and the engineers would call the speed of the system performance. So that's how deep the differences can go. So this often creates tension. If you have one group that focuses on one quality attribute that trades off with another that the other team focuses on, you have to find a way of reconciling that and actually being able to establish a good development process. So the question is, when team from two different organizations with different incentive structures collaborate, can we design our software architecture to avoid the tension between the quality attributes that we know ahead of time, ideally the different teams will focus on? And as the title of the talk hints, this one approach that we took was to facilitate that sort of architecture approach through microservice architecture and using the technique of architectural hoisting. So to briefly define those, I'm pretty sure if you ask 3 different people what a microservice is, you'll get 3 different answers. So let's go with one that was from a top Google result. So a microservice architecture is an architectural style that structures an application as a collection of loosely coupled services which implement business capabilities. And to give this a visual, again, something that I pulled from a top Google result, with the source here, of course, because we're honest people here. A monolithic architecture, generally you have everything in one large application that runs as a monolith. Meanwhile, in a microservice architecture, we might take those individual components and stand each of them up as services, where each microservice speaks to as many others as it needs, and we have lots of little pieces of the program distributed in this way, which gives us various benefits in various situations. So this, going with the microservice architecture, which we already had precedent for in this case study that I'm going to talk about, gave us an opportunity of trying out the combining of that with a technique called architectural hoisting. So I'm going to quote George Fairbanks here. And architectural hoisting is the direct ownership, management, or guarantee by the architecture of feature, property, or quality attribute. And in particular, it lets developers depend on the architecture for the hoisted feature, property, or quality. So this returns to the question, with these definitions in mind and these perspectives, is there any way we can use these so that when teams from different organizations work together, we can adopt an architectural approach to reconcile this tension between, this possible tension between teams and the way they work? And we do this, or we try to do this, by hoisting certain quality attributes into the architecture itself. So we'll simplify a little bit. And let's say we have, as I said, a research team and an engineering team. And let's say that we know ahead of time that the research team is going to focus on accuracy. They're going to focus on developing the algorithm, on pushing the state of the art, while the engineering team will be concerned with more product type concerns. And let's just say for now, to simplify the conversation, that their main concern is performance. So is there any way that we can design the architecture to have as many quality attributes as we can make it have, in such a way that we can have both teams working and pursuing their own incentives, but working within the architecture so that they don't have to deal with this tension, and that these things are actually, that the architecture makes it difficult for either team to actually damage the system or prevent the system from having these properties. So to make this concrete, let's go into the case study of what happens. So this was a project that was building on top of an existing platform that was in production. And in particular, we had a novel AI task to be solved. Now, all we knew was the inputs and outputs. We didn't actually know how it was going to be solved, what the concerns of the application would be, what different types of data stores or resources it might need. And essentially, 2 teams were picked, put together, and said, you two, make the system, find a solution, make the system, ship it. So using this method of architectural hoisting, what we tried to do was the engineering team tried to design the system so that we could iterate on the system design itself and focus on things like performance, fault tolerance, and things like that, while research could just pursue their incentives and focus on state-of-the-art improvements. In particular, this was made more difficult by the fact that the algorithmic solution actually had not been developed, but there was a tight deadline and we had to start. So we had to build a lot of flexibility into the architecture to allow us to actually fulfill all these goals. We didn't have time to be losing friction to figuring out, let's say there is some sort of improvement made in a prototype. We don't want to spend time re-implementing the prototype. In particular, can we have the research team just writing code that ships directly to production? So this is, we went through a lot of redesigns in order to do this. I'll just breeze through a couple. I just want to illustrate how much this changed. So over the course of 3 months, we went from this initial design where we have these just visually looking at the shape of it. Within about a month, this got rearranged, the architecture diagram, to look like this. We rearranged it again after we figured out more concerns. And we finally ended up with this final design. And all of these redesigns happened in about 3 months. Now, this was made easier because we were able to repurpose microservices because they implemented one business capability, and all we changed was how these pieces communicate differently with one another. So actually, I forgot to pull this out. So we'll go through this a little bit. There were some general patterns we found that were very useful to mediate the sort of approach we had, and I'll go through them after just describing what the subsystems are here. So what was this task? We have some sort of data that comes in, some documents in this case, and we have an ingestion subsystem here where we essentially have to put those through an ingestion process, extract some data from them, do some processing, some pre-processing to get the data in the format that we want. We want to have messages, or we have messages of incoming documents as they come in. There's some data extraction here in a kind of a standalone component. And a document store. So later, we have all of this data that the customer has given us, and later a user wants to extract some information from it, and they would give 2 or 3 examples of the sort of information they wanted to extract. And the idea was that we would implement a way of extracting other types of information of that sort from the rest of the data set just by extending the pattern of the examples they gave us. So the way that we set this up, we'll go into this in a second, is each of these algorithm boxes refers to a different approach to solving the problem. So one of these was worked on by the research team, one of these was worked on by the engineering team. And we tried to encapsulate this work into these components so that we could try to encourage, so that we wouldn't require the research team to be doing the sort of work that they're not incentivized to do, that they don't want to do, such as testing of the entire system or worrying about data ingestion or data management or any of these things. So like I said, there was generally one ingestion system. This mostly we designed on our own, but with obviously input about what the data needed to look like. There's a training subsystem where as data changes, we have basically a proxy to a high-performance compute cluster where we have some model storage and some model serving so we can actually query the model later at runtime. And of course, the query time system where we would get some example input from the user, do some analysis, and extract the information from the model and return it back to the user. The patterns that we use in order to do this are fixed interfaces for multiple provider backends. So each of these implementations has the same exact interface, and they solve the same problem but in different ways. So what are the quality attributes that we've actually encoded in the architecture here by having as many different backends as we want with the same interface? We have extensibility. For one, we can implement new functionality or new modes of analysis in the backend here. And when a request comes in and we fan it out, they all respond and we collect it all and put it in a database. This enabled experimentation. This also enabled fault tolerance. So we had a much decreased worry about fault tolerance. So let's say there are some edge cases in the research implementation that have not been ironed out or haven't been handled, because that's just not something that team generally has to do or is incentivized to worry about. If that happens, then we have another component ready to take over and return some sort of input so that the system as a whole is not down. So we have just maybe degraded service, but that is a degree of fault tolerance. A second pattern that we can extract from the way we did this was message queues for events. Let's say new data comes in that we need to process and train a new model on. So by doing it this way, we encoded scalability into the system. So we don't need necessarily, let's say that there's some sort of data extraction that comes in and it's a little bit slow. Well, we can just add more workers that all read from the same message queue and give us the ability to scale up as we need to. And this is actually not so much by our design, but by microservice architecture itself, because you can always add more replicas that back a service. We also have pub sub for state changes. So let's say that we have a team implementing the data analysis or model training for the data that comes in. But we don't want to have them worry about how to read the data, about data backups, about cleaning up data that's old, about all of these things. So rather than having them worry about it, we let them focus on what they, again, want to focus on. And every time there's a state change and we handle it, we have a pub sub mechanism, and it just notifies the various implementations to actually pick up the new data and use it. So now we've built in modularity and reliability into the system as quality attributes by just taking away this concern and putting it in the architecture itself rather than in any one particular component. Generally also useful, proxies and facades. So rather than having to have everybody figure out how to use this high performance compute cluster, what the parameters are, managing credentials, where the object storage is going to be, the permissions, the file storage, we just encapsulate that all in a proxy. So now all that another team has to do is it writes the actual training script and just submits it, and we take care of everything else. So this is all abstracted away, which also gives us separation of concerns. And again, lets the iteration on the algorithmic implementation solution to iterate, to proceed without worrying about all of the rest of these things. So at the same time, we have the research organization pursuing its incentives and what it wants to do by just focusing on that algorithm and everything else being abstracted away. Meanwhile, we can take the time to optimize whatever other components are slow or need more testing or need better error handling. And so both teams are able, because this is what both teams are naturally inclined to do, they're enabled to do this by the architecture, and both actually proceed doing that full time with full focus and without getting distracted by figuring out code handoffs or reviewing each other's code and disagreeing on code style or testing practices or anything like that. So the results of how this actually all worked out. So the architectural flexibility that we built in using this approach, which was enabled by a microservice architecture, it minimized the impact of changing requirements and scope creep, which happened as it always does. The final product had a cohesive design, and we'd argue pretty much all desired quality attributes. We had performance, we had accuracy, we had scalability, modularity, all of these things. In the end, the AI team, the research team, submitted their work to the journal because they were able to, even though this was a relatively short project, they were able to focus full time on what they needed to do. So even with just 6 months, which is relatively short for a research project, they were able to improve the state of the art and submit to the conferences that they are rewarded to be submitting to and going to by their organization. And throughout the entire process, we had significantly reduced communication and management overhead. So since we had well-isolated components with clear responsibilities and the various concerns being actually lifted in the architecture, and we don't have to argue about the performance of this or that or how various, or what the fault tolerance will be or whether these edge cases are handled. Everyone just naturally focused on what they are inclined to do and have experience doing, so there was very little overhead there. And this also meant that everybody was happier doing the work that they did. So nobody had to actually be stuck doing work that they felt they shouldn't have to do or wasn't normally their responsibility, which you always have to do to some degree, but this also meant that people were just happier doing what they were doing. Some downsides. So we actually went a little bit too far with a decoupling of these teams. So we had, there was a period of time where we hadn't really touched base very well for 2 or 3 weeks. And we met and we realized that both teams had designed mutually exclusive solutions to the same problem because there was just no communication, that both had identified this problem and both were working on it. So this flexibility allowed a loss of synchronization at times on requirements. So there was miscommunication there because we got used to kind of working on our separate components and just trusting the other team to be doing what they're doing. And sometimes there was some miscommunication on design decisions. There were 1 or 2 times when the responsibilities of a certain component weren't clear to one team, well, one or the other. So if we could actually go back and do it again, how would we have improved it? One is to keep some sort of record of the architectural decisions that were made, periodically as they are made, especially when each of these redesigns happened. Because then we would have a record where we could just reference it, send a link over to whoever needs to get caught up. And we actually did very little cross-team code review or any sort of periodic knowledge sharing throughout the project. So in the end, when one team had some slack towards getting closer to the deadline, it was actually unable to help the other team finish up on something they were behind on because we weren't familiar with the code base, and then the law of adding more people to a late project makes it later would have kicked in right there. And finally, I tried very hard to eliminate the need for any sort of formal project management role, but this experience convinced me that you do need some sort of manager on most projects, especially if you have more than one team. So I finally internalized the need for that to be there. So to kind of recap, what's the main idea here? We start with the observation that teams in different organizations have different incentive structures, and that those incentive structures may cause those teams to naturally prioritize different quality attributes. And in a cross-organization collaboration, these may be in tension with one another. And so one way of trying to resolve this is to use architectural hoisting to hoist certain quality attributes in the architecture itself so that the individual teams don't have to worry about it and can naturally pursue their normal ways of working. And that this is particularly easy using a microservice architecture. And finally, with an observation that once this gets going and people get comfortable with it, they can actually lose communication more than they should. And this is something to watch out for. This architectural approach to encouraging collaboration is not magic. It comes with its own risks, like any other methodology. It needs to be executed with care. And that's all I have. Thank you. So, are there any questions?
Can you go back to, I think, the third or fourth slide? That's the ISO
Sure.
part of the definition of QA.
The chart?
Yeah.
Sure, this one.
So I have a question about how the responsibilities were actually split up. Was it simply by the nature of this is research, this is engineering, high scale? Like, could you talk a little bit about that actual modularization?
Sure. So let's go back to that diagram, which I did kind of breeze through. Generally, yes, it was. What we tried to do is identify what at the end of the. We try to identify what sorts of skills are most developed on each team and what they are naturally going to be working on the most, and then try to design the separation of concerns so that different teams could own different components entirely. So in particular, like I said, we actually, in this case, we were able to come up with a simple but fast and reliable implementation for the problem at hand ourselves, and let the research team focus on another one. So this was entirely their component that they owned, just based on that to let them iterate and have their own playground. Towards the end, we did come in and help add some more robust testing to make sure everything was working properly. But yes, it was very much based on what their roles were overall within their organizations.
What is the role of sidecar here? Is that the research team?
That is just, I kind of repurposed this slide from an internal presentation and took away the names of things.
Yeah.
This is kind of like a mini proxy to send a particular customer's request to their model and not somebody else's. It's kind of a little, it's not particularly important to the overall.
Okay. I just saw it was like bypassing this proxy.
Yes. You can pretend that these arrows go straight there.
How did you keep track of your QAs?
So for the accuracy, again, this was the benefit of letting people fulfill the roles that they naturally have from within the organizations. So the accuracy, there were routine accuracy tests being run against the research team's component that they would just, nobody had to tell them to do it, they just did it. So they're keeping track of that themselves. On our hand, we already had load testing and performance testing habits because of what we do normally. So we would just apply that to the entire system and then try to identify bottlenecks and improve those. So again, just very naturally, people did what they are naturally inclined to do and used to do. I should mention that these were relatively mature teams. They were not fresh out of school hires, right? So each team just took care of its own concerns.
So was each component set up as a microservice in terms of actual development and?
Yes. So separate repositories on GitHub, everything or in source control in general.
So it's not just a model of how the responsibilities were split up, but it's literally microservices.
Yes. One thing that helped a lot is because we had precedent for microservice-based architecture, so we had some templates we shared. So things like setting up best practices for certain libraries was already established, so that we kind of hit the ground running and we didn't have to learn a new framework. So that was very helpful. And perhaps actually one of the lucky things that made this work within a short period of time.
How did you handle change management across all of these services?
More specifically?
Made a change to one of the services. How did you tell other services that something was going to change?
By designing the responsibilities of each up front and with a strict RPC API, so this was not JSON, it's very well defined and difficult to change. And that was just because we had this design up front of the concerns of each. Everybody, when we found out we needed to make a change in one service, we just naturally knew that, oh, we need to communicate this to the other team because they're calling it for this purpose. So there's two separate teams of maybe about 5 people, so that happened more easily. Maybe with a larger team, that would be, things would fall through the cracks more easily.
Thank you.
Yes.
I'm not sure if these organizations have bought into SOA in the past, but I was wondering, or microservices in the past, but I was wondering if you had any challenges or pushback from like ops, IT, et cetera, and getting numerous services like this deployed. I've run into issues in the past where they're like, here are these 10 services that need to go up to make this application work, and they essentially have a bad time.
We did our own DevOps, our own provisioning, our own quota requests and all of these, so we kind of just said we need this much RAM and this much CPU, and we got to do whatever we want with it.
Sweet.
Yeah, we had a lot of freedom.
Was security ever a factor when you focused on?
Because we were adding a new system on top of an existing platform that we had, a lot of those problems had already been solved. So, for example, the engineering team was already its own certificate authority and had figured out key management and things like that, and just built that into the template into the microservice template that was reused.
What was the load on the system? How many?
At first, 0.
Wow. Once it goes into production.
Not very high, actually. You might argue that we kind of went a little crazy with it. The part that I didn't mention is that even though we had everything up and running, very soon after everything was finished, there was an internal reorganization. There was nobody left to go on call for it. So it's just sitting there running and staging, but not production. But we did try it out with collections of millions of documents, and then it flew, tested it out manually. It could have handled a lot of load.
So with all the cross-service communication, did that have like an impact on latency? Was there a specific latency requirement?
So if you actually sit down and look at any particular event in a system, such as querying a model or updating a model, there's never more than 2 or 3 hops, and each hop is on the scale of microseconds.
And that was thought of when the design was being put together, that each 2 components should not have more than 2 to 3 hops? No,
I just made that up, actually, or I just noticed that in response to your question. Like a query goes in through here, and it just hits the model. Ingestion, I guess, has a couple, but you have the message queue, you have this, and it gets processed. It just kind of came out that way from the design.
So what I'm trying to get at is if someone with less experience or just not knowing what they're doing try to use this model, it's easy to kind of get that latency issue in this kind of model. At least I think. And so, like, what
Maybe.
recommendation would you have?
Well, when my coworker and I, who were co-technical leads on this, sat down and tried to look at it and see if we could extract any principles from it. We ended up laughing after about 10 minutes because all we had written down was encapsulation and abstraction. So
Right.
just a strong understanding of the problem. Well, not even that, because like I mentioned, it went through so many redesigns. It's really just having a strong separation of concerns that facilitates that. And we did, with all this emergent complexity in the inter-service communication, I mean, you have state changes coming in on a queue, and you have pub sub, which means you have synchronization. You might have potentially lost messages, although it's really unlikely. You might have things going out of sync. You might have some replicas with some of the storage, having eventual consistency, things like that. It took quite a while to iron all of those out. So even though each component is simpler, the complexity has to be somewhere, and here it's in the architecture.
So are all of these lines RPC calls, or
Yes.
are they using other?
We use gRPC for everything.
You talked about one of the possible improvements being recording your architectural design decisions.
Yes.
Do you have like an idea of if you had to go back and do it again, like I don't know what like framework you might use to record the architecture?
So this was, the sad part is that we already had an internal template for this, and we kind of just didn't do it because we had to move very quickly. Well, that's not an excuse. We just didn't do it. If you actually Google the phrase architectural decision records, there's a few blog posts that give a template that we use pretty much directly with some simplification. And there's actually a few talks floating around online about it too. One of them given by my colleague, Michael Keeling, who will be speaking here apparently in a couple months. So you can, he was the one who actually brought those into the team way before this project started.
How many people were involved in this project?
So the engineering team was 4 or 5. It was 5 full-time engineers, a couple from time to time consulting. They were distributed among Pittsburgh and Denver. The research team was a team of about 4 or 5 again, and they were in New York City. And we had another team. Oh, I guess we also had a design team that was coming up with the tooling for all this at the same time. That was just a couple people. They were in the same office as us in Pittsburgh. And there was another team that we would consult with because they had another application that helped drive the requirements and some of the database design for us in San Jose. That was about a team of 6 people, I want to say, but we really only talked to 1 or 2.
Slightly less technical question. You said at the end, in retrospect, you wish you had some project management or some project manager over things. Project managers tend not to come with technical skills. What are some of the minimal technical skills your ideal project manager going into this project would have had?
Just ensuring routine check-ins across team, and just keeping track of, let's say, one team discovers a new requirement or a concern that wasn't there, and making sure that gets communicated. Because often when you say, oh, I didn't realize I had to do this, and you go off and you put up the code and then you move on. Which we tried to be good about that, but from time to time, things fell through. This case was interesting because this was a special project, and the 5 engineers picked were all from different teams, and each had a different manager. So this team had no manager in the end. And that's why we felt that lack. Then there were other things like coordinating security reviews and things like that, because there's certain process things we have to do that, at least in our office, our managers usually take care of organizing all that and setting it up and synchronizing with other teams. So I guess maybe it's a little bit more than project management, because this is quite a large organization. There's a lot of external communication that needs to happen.
Since you didn't adopt the ADRs, did you end up doing anything else, like, or organically to communicate your decision making?
We were a little bit we were fortunate with the team makeup because the maturity of people on each team were the sort of people that naturally would, when they noticed something I needed to communicate, would naturally just call a meeting with everybody. Just very proactive. So that kind of just happened organically. And that probably also was a large reason that we were able to actually stay on track without having any sort of management overhead at all. So if I had 5 people hired out of school for one team and 5 people hired out of school for another team, I would probably want to set up some sort of process first for them to follow. I don't mean to pick on college hires. I'm just saying that these habits are ones you develop as you start working, and everybody had.
Or engineers who are just simply difficult to work. Not one of those two.
True. I'm going to go back to this one because I like how it looks. And I found this by Googling JavaScript. Is there anything else? Let's leave it on Y. Okay. Well, thank you, everyone.
Thank you.